Okay, here's a little extra review from Chapter 8 with the confidence intervals. Just want to remind you, go over this little thing we started in class, getting the conditions and focusing on how means are similar to proportions in some ways. But again, the second condition, the normality, is different for both. Independence can be the same, and then of course the formulas. So kind of spend some time making sure you have the clear understanding on the both of those. Um, and just kind of remember, anytime you have a p hat or a p or anything, that's got to be a proportion. So um, if you don't, if you have a sigma or a standard deviation of a sample, that's going to be more of a mean, like an S sub x and whatnot. So give those a good look. Make sure you have the conditions down. I did want to set up another example here, um, running through a little sample problem. So let's say we have done a test, 18 randomly selected rolls of generic brand toilet paper, and we counted the number of squares required to clean up a small water spill. Okay, so we have 18 different little tests. The first test took 29 squares to clean up the water. The second test took 20 squares, and so on. Okay, and let's say we want to go ahead and find a part A here. Can we find a 90% confidence interval for the true proportion of rolls that require more than 25 squares? Okay, so we're looking for a certain condition here. We want more than 25 squares. Okay, so let's look at our sample. We have a sample. We can get an estimate of the proportion just from our sample. So in our sample, more than 25, we had 1, 2, 3, 4, 5, 6, looks like 7 out of the 18. So we have an estimate here, okay? We can use a p-hat of 7 out of 18. Okay, and if you want to convert that to a decimal, that's fine. I'm going to leave it as a fraction because I think it's going to be a decimal that goes on forever that I don't want to round. So let's see if we can figure out some conditions, see if they're met. We can go through the process. Again, we know n is 18. Um, so our three conditions, we need a random sample, and I think that one was given to us. Okay, so the sample's random, so that's good. It represents all rolls of toilet paper from this generic brand. Now, do we have the normality condition? Okay, with proportions, that's your n times p hat being greater than or equal to 10, and n times 1 minus p hat. So this, again, remember, these go back to the binomial distribution chapter. In order to get the binomial distribution to look normal, those conditions needed to be met, and this is kind of a direct consequence of that. So let's see what we got. We know what n is. We know what p hat is. So n is 18. P hat 7 out of 18. Is that greater than or equal to 10? I think we can kind of tell. The 18s will cancel out. That'll give us a 7. And note, that's just how many successes there were. There were 7 successes. That's really what n times p hat is. It's how many successes you have. So you need at least 10 successes, and you need at least 10 failures, which would be over here. Now, in our sample, we didn't have enough. Okay, so in a problem like this, we would just say, we don't know that it's normal. We couldn't do the confidence interval. Okay, so sometimes that happens. So this one we would just say no, we can't find the interval. Let's go ahead then, though, in part B. It's kind of a continuation here. Let me move this up a little bit. Let's say, assuming those conditions were met, how large of a sample would we need? Okay, so we're looking for n. To construct a confidence interval, 99%, with a margin of error of 0.1. And they're telling us to use p hat from the data. So we know p hat from above was the 7 out of 18. Okay. Now think about this. If we didn't have the sample yet, and we had a problem like this, and we did not have a p hat to use, that's when you would use 0.5 for p hat, because that gives us the most wiggle room. It's like the best possible scenario to make sure we don't underestimate anything. 0.5 is like the optimal one to use in this type of problem. But we're going to go ahead and use the 7/18, 7 out of 18, because we had that. Okay, so we just got to remember, with confidence intervals for proportions, the margin of error is all the stuff after the plus or minus. So in this case, it's going to be some z star, which we'll talk about. That'll come from the confidence level. And then it's going to be times the standard deviation, which is going to be p hat 1 minus p hat all over n. Okay? And they're telling you what they want the margin of error to be. Okay, so we want to have 0.1 equaling that stuff. So let's start plugging some things in here. 0.1 is the margin of error they want. Z star, that comes from the confidence level. So at 99%, that is 2.576. Okay, 2.576 Z star. Okay, remember that comes from an inverse normal if you need to come up with that. The square root of p hat, I'm going to keep these as fractions. 7/18. Okay, 1 minus p hat would be then 11/18. Okay, and our sample size n was 18. Oh, I'm sorry. Let me catch myself there. 18 was the sample we had. We're doing a different type of problem. Sorry. We are trying to find out, what sample size we need in order for the margin of error to be 0.1. So don't fall into that trap. Normally when we do these problems, you don't have a sample and you don't have the data in front of you, but I just wanted to kind of connect this to that one. So pretend like we don't know n, okay? Because most of the problems you will not. Okay, because that's what we want to find. So we got to do a little algebra here. Okay, so let's go ahead and divide both sides by the 0.2576. Okay, so I'm going to divide by 2.576, and dividing the right side by that will just cause this to not be there anymore. Okay, that'll cancel out. Okay, so we have that 0.1 divided by 2.576 equals the square root of something. Our variable is buried under a square root. Let's go ahead and square both sides. Okay, so I'm going to let me just rewrite this here, that over that, all squared. Okay, my square root's going to go away on this side. It's going to be 7/18 times 11/18 all over n. We want to solve for n. Okay, so now again, my variable is in the denominator of a fraction. I'm going to multiply both sides by n to get it out of there. So n times all of this stuff. And we are no longer dividing by n on this side, okay, because that would cancel out when we multiply by n. Okay, and then finally to finish this side, I would just divide both sides by this 0.1 over 2.576 all squared. Let's divide that side by 0.1 over 2.576 squared. Okay, and that is going to get us n. Okay, because that cancels that. So we got ourselves a nice little calculator problem. Okay, so let's do that. We have 7/18 times 11/18. So we still got to be careful on the calculator. So the numerator there is the 7/18. Let's see if we can get this large screen. Come on now, large screen. All right, might have to just go and do this here. There we go. All right, so 7/18 times 11/18. Okay, and I'm actually going to press enter. I'm going to get that as an answer. That thing needs to get divided by the denominator, which was the point, let's see, I forgot my numbers here. 0.01 over 2.576 squared. So let's take the answer that we have, divide by 0.1 over 2.576. That whole thing was squared. Okay, and I just put the extra set of parentheses just to make sure we're going to divide by that entire thing. So let's take in the 0.2376 dividing by the denominator, and that's given us an answer of about 157.7. Okay, so that's n. N would need to be 1. If n was 157.7, our margin of error would be exactly 0.1. Now again, we're not going to probably sample 0.7 of a roll of toilet paper, So we're going to round up. Okay, even if it was 157.1, we're going to round up. Okay, so we're going to say n needs to be at least 158 rolls of toilet paper. Okay, always answer in context. It's a good idea just to um, relate back to the question. Okay, so there's find the sample size problem. Okay, now let's do one other one. I do want to do a confidence interval for this, um, but let's do it for a mean here. Let's say we want to find a 99% confidence interval for the true mean number of squares required to clean up the spill. So let's go back to our original data, um, and let's find the interval for that. Okay, so do we have a random sample? Yes. Is it normal? Okay, so random was a yes. They gave us that amount. Okay, normal. Okay, we have a few options for means. Our sample size could be 30 or more. That wasn't the case. We had 18. They could tell us the population's normal. They didn't. Okay, so we don't know that yet. So that leaves option 3 here. Let's take a look at the normal plot of the data. Okay, and what you want to look for is, are there any major outliers, any major skewness, or actually the easiest way is to make this normal probability plot and look for a linear pattern. Okay, that's going to be the best way to do this on the calculator and quickest. So I went ahead and put the values into a list here. So that should be our 18 values in L1. Okay, and what I want to do, I want to check to see if they look fairly normal. I'm going to go to stat plot. Okay, and go into the first one. And the option's already chosen for type. It's the one on the bottom right. That's a normal probability plot. Okay, so be careful. It's not a scatter plot like the first option. We don't have x and y's. You know, we just have one list of data. So I'm going to go ahead and do that. My data is in list 1, and I'm going to go ahead and do zoom 9 for zoom stat, so it'll fit my list. Okay, and it appears to be, you know, somewhat linear pattern there, pretty good. You know, it has a little bit going on up here, but for the most part, you know, it's fairly linear. It's not like a quadratic parabola or some crazy looking graph. So just mention something like that. Okay, mention that you plotted the data. Maybe just do a quick sketch of that plot. So since this show is linear, um, we are able to assume normality condition. Okay, so we got condition 1 given to us, 2 we just checked, 3 independent. We had 18 things in our sample. Do you think there's more than 180 rolls of toilet paper in the world, or from this particular brand? Yes, so we're going to assume that. Okay, so we will assume that capital N is greater than or equal to 10 times, in our case, lowercase n was 18. Okay, so we're going to assume there's a lot of toilet paper out there. So let's go ahead and find the interval. Okay, we got our conditions met. Okay, so we need a sample mean to give us an estimate to start with, and they did not give us a sigma, which most of the time they will not, so we're going to use the sample standard deviation. Okay, so our estimate, we're going to do plus or minus. We're using a t-star because we don't know sigma. We're going to use s sub x over root n as our standard deviation because we don't know sigma again. Okay, so again, to get the x bar, okay, and the s sub x, those are going to come from one variable stats. We have the values in the list already. So let's go back there. Okay, let's get out of here. We're going to go back to stat, calculate one variable stats of list 1. Okay, and we're going to get our sample mean, x bar, we're going to get our sigma, s sub x. So we're going to use both of those numbers. So 24.94, and we will use the 2.859 for standard deviation. Okay, so let's do that. We have, again, the sample mean, our point estimate. You know, the best thing we have to use, 24. I'm going to round it a little bit, plus or minus. Let's get the t-star in a second here. The standard deviation again was 2.859 over root 18. Okay, so now the question becomes, what t-star? Okay, so let's think about this. We need We wanted, what, a 99% level, I believe? 99%. Okay, it was given as the confidence level. So pretty big one, 99%. We have 1% of the data missing. Half of that's up here. Half a percent. 0.005, 0.005. Okay, the t-star is going to be basically the kind of like a z-score, but it's a t-score of this upper value. Okay, and again, we're using t because we did not know sigma. We substituted this value, the sample standard deviation, so we have to use t. So to get t star, you can either use the table in the back of the book, or it's much better to use the calculator's inverse t, area below. Okay, area below is this guy and this guy. Okay, 0.995. Okay, and then the um, degrees of freedom will be one less than the sample size. Okay, so in this case, degrees of freedom is going to be 17. Okay, one less than the sample size. Okay, and that calculation will give you the t-star that we need to use. That'll go right here. Okay, so let's do that real quick. Under distribution, second distribution, inverse t, there it is, fourth. Okay, we were using 0.995. That was the area below our value with 17 degrees of freedom. Let the calculator think for a second, and there it is, 2.898. Okay, again, 3 decimal places is pretty standard to round that to. So that'll be 2.898. All right, and we should be able to do our calculations now. Okay, so let's just do it the long way, and then we can verify them on the calculator. The long way would be to actually go and type it in. Okay, let's do our sample mean, 24.94. Let's do the plus first. It's 2.898 times the standard deviation. Okay, we're using the sample value of 2.859 over the square root of 18. Okay, and that should give you the upper end point of the interval. Okay, a little trick to get the lower end. It's basically the whole thing except there's a minus. So second enter, repeat what you had. Go and change that plus after the x bar to a minus. And that's your lower end point. Okay, so this is like the do step. The shortcut way to do this step, okay, with still showing all the other work, is to go under stat, over to tests. Okay, and we're doing intervals still. Tests will come up next chapter. So scroll down a little bit. We could do a z interval. We didn't use z though. We used t. T interval. Okay, again, our data. We have all of the data into list 1. Okay, if you didn't have the list, let's say they just gave you a mean and a sample standard deviation, you could go over to stats and type in what those values are. Okay, and these are the values I think from our list, but if they just gave you some mean and s sub x and n, throw those in there. But let's do it as data because we have the entire list. Frequency, we're not going to mess with that, just stays as 1. We just want each value to count once. And then use your confidence level as a decimal is 0.99. Okay, and this should give you the same two numbers that we got, the 22.99. So it's a little bit more exact because this did not round anything, but we were fine the way we had it to. Okay, so then we just need to finish with a conclusion saying, we are 99% confident. You just want to finish with an interpretation. We are 99% confident that the true mean number of squares required to clean up the spill is between, okay, and then those two numbers we got, the 22.987 and 26.89. Okay, and again, I might round it a touch different, but give me your conclusion, and that's that.